At the Earth's surface, the projectile is launched straight up at a speed of 10 kilometers per second. To what height will it rise? Ignore air resistance and rotation.
So, we're going to take Travis. We're going to create a catapult. This will be much more fun with a catapult thing. We're going to launch him vertically upward with a catapult, maybe a trebuchet. Can you launch someone just vertically? Yeah, it's going to be a large trebuchet.
At 10 kilometers.
At 10 kilometers per second.
That'd be a crazy. At 10 kilometers.
And our goal here is to figure out what Travis's final height will be. So here we have the ground. Actually, we'll do this. We'll just do a teeter totter. Here we go.
Cheers.
We'll give ourselves. No, we'll go the other way. So, yeah, we'll have to drop something very large. So here you are, Travis. Travis, we'll give you a helmet. If you're going to do this as well, we'll give you a cape. Congrats. We're going to take from a very large building. We're going to drop something off the top of the building such that it will land on here. We're going to give ourselves a mechanical advantage so that we can launch you vertically upward with an initial velocity of 10 kilometers per second. And the question is, if we looked at this from a more global perspective, there you are. So height final equals question mark. It's got a cape. It's got a cape. It's got everything you need. Sorry, there was the last statement, Emily, in there. I said something about
Says ignore air resistance and the rotation of the Earth.
class. Is there friction? No. Is there a force applied? Therefore, not UAM. Okay, actually, let's point out why we can't use UAM. It's a fair question. Why can we not use UAM? So,
The force of gravity changes as we leave there.
well, we'll say the acceleration, because force of gravity causes the acceleration to change as we leave the planets here. So we cannot use uniformly accelerated motion because the acceleration is going to change as a function of position. However, there is no friction, there is no force applied, therefore class. Conservation of mechanical energy. Mechanical energy initial equals mechanical energy final. Here's the initial point, here's the final point. Class, we need to set a zero line.
It's preset.
It's preset. Where is the zero line? Infinitely far away. Mechanical energy initial. What sort of energy does Travis start with? Huh?
What?
Yes, what sort of energy, mechanical energy does Travis start with right here?
Well, he's on a giant catapult.
Does that help?
I want to say, I don't know, his initial velocity is kinetic energy.
So he has kinetic energy, I agree. Anything else?
I'd say no.
Okay. What sort of energy does he end with then?
Gravitational.
Gravitational potential energy. Any kinetic energy?
Nope.
Nope, because he stops. We're fine to figure out the height final. Who can tell me what's wrong with it? John?
Isn't there potential gravitational energy in the first part?
There
because
is
of the
gravitational potential energy initial. Remind me, class, where's the zero line? Infinitely far away. So he has gravitational potential energy initial. What is the equation for gravitational potential energy initial, Zach? Okay, let's be careful. This is, what are the two masses here? Good, mass of Travis and the mass of the Earth. Okay, R is going to be here, the radius of the Earth. right? Okay. What's missing? Miller. The negative. There are two really popular things to forget about universal gravitational potential energy. It's hard. I might be hard pressed to say which one's number one and which one's number two, but clearly forgetting the negative and adding a square. So please be very careful. Kinetic energy. 1/2 the mass of Travis times the velocity of Travis initial squared equals negative big G, the mass of Travis, the mass of the Earth, divided by the rate, or R final is what I'll put there. Everyone brought mass of Travis to the party. Piece of trivia. Mr. Palmer, sophomore year in college, at the Nectarine. It's a local bar that I think no longer exists. Every Wednesday night, they would have disco night. And if you dressed in disco clothing, you got in for free. I frequented that very often. So we have, let's see. So we're trying to figure out, we have all this information, don't we? We're just trying to figure out R final. So we have big G, 6.67 times 10 to the negative 11. The mass of the Earth is 5.98 times 10 to the 24th. You'll find that on your page 399. The radius of the Earth is 6.375, I believe, times 10 to the 6th. Plus the velocity of Travis, which we need in meters, 1/10,000 meters per second. That quantity squared divided by 2 equals negative big G, 6.67 times 10 to the negative 11 times the mass of the Earth, 5.98 times 10 to the 24th, divided by R final. Please give me R final.
What, did you give up?
Yeah.
Wait, yeah, okay. 6.375 times 10 to the 16. Maybe. It's possible.
We'll see. Other thoughts?
Yeah, that's what I got.
I didn't even move our final.
Oh, yeah. No. I think it's
3.173 times 10 to the 7. That's what I got.
I got that. Yeah, I got that.
So Brandon's wrong.
So the altitude then is going to be equal to R final minus the radius of the Earth. So 3.173 times 10 to the 7th minus 6.375 times 10 to the 6th. What do we get?
2.535 times 10 to the
1, 2, 3, 4, 5, 6, 7.
Yes? 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 Okay. In other words, 25,400 kilometers. Okay. What if that, okay, actually, let's start here. Travis, what's going to happen to you now? You're just going to get pulled back down. What if this is not enough for us? What if we want to get permanently rid of Travis? Because the truth of the matter is, if you could jump fast enough, you could leave the surface of the planet, right? So this is not enough. So let us figure out the escape velocity of the planet.
Oh, no black holes.
Let's see how close we were to being able to get rid of Travis with our giant catapult here. Travis, you know our feelings. The escape velocity. So where does this change the problem? Hillary. Our goal is the escape velocity is to figure out the minimum velocity necessary to remove Travis from the planet permanently. The approach is very similar. Where does it divert from what we were doing?
We wouldn't have final potential negative gravity.
Because where would he be?
Infinitely far away.
He would technically be infinitely far away, and what would his velocity be at that time?
What, sorry, what was the question?
So what's his velocity going to be when he gets infinitely far away from the planet? 0. Notice if we get the perfect escape velocity, his final velocity when he gets infinitely far away from the planet is going to be 0. The truth of the matter is that would take forever to happen as well, right? Because he would just slow down forever until he got infinitely far away. There's a bunch of fun things to think about. But if you go slightly greater than the escape velocity, then he's going to end with some sort of final velocity. So we're trying to figure out the escape velocity. So what we get here is negative big G, the mass of Travis times the mass of the Earth, divided by the radius of the Earth, plus 1/2 times the mass of Travis times the velocity of Travis initial squared equals 0. Our goal is to figure out the escape velocity. Go ahead. Wow, people.
Wake me up before you go, girl. Don't leave me hanging on like a yo-yo. Wake me up before you go, girl. I don't wanna miss it when you hit that high. Wake me up before you go, girl. 'Cause I'm not planning on your solo. Wake me up before you go, girl. Take you dancing tonight.
Who can name the band?
Oh, I know.
No. I'll give you a hint. It has an exclamation point in it. It's all caps.
It's Wham,
It's
isn't it?
Wham.
Oh my god. Jumped out of it.
In other words, the escape velocity is equal to the square root of 2 big G mass of the Earth divided by the radius of the Earth. So we can figure out the escape velocity is going to be 2 times 6.67 times 10 to the negative 11 multiplied by the mass of the Earth, 5.98 times 10 to the 24th divided by the radius of the Earth, which was 6.375 times 10 to the 6th, the square root of the whole thing. It's a big G.
Is it 11,186?
11,000.
Yeah, from retirement. Is it? Yeah, is it?
11,000.
Wait, you got it wrong too,
186.
so we need another source.
So we have that in meters per second, so 11.2 kilometers per second. We were almost there. So close.